So the point today is to discuss epidemic models which have some kind of structure, which is, and I will show you that you can kind of model behavioral aspects with compartmental models in a very, I mean, not very precise way, but anyhow. So, and we will proceed with an example, okay, a simple case. And the case is that the population that you are studying will be structured by risk factors. So there are many structures you can have in a population. For instance, age. So you can have gender, sex, gender, and socio-economical aspects, behavioral aspects, and so on. You could pose the question, yeah, what should I take? Should I actually take into account when I write a model? So the aspects that you should take account usually are such that they are important from the epidemiological point of view. So, for instance, we have studied a lot of models and so on. We have never separated the population between males and females, masculine, feminine. Right? Never, because many, for instance, take COVID. Okay, there's no point of separating men from women because, well, it's the same thing. So it has no epidemiological impact. Right? In more realistic models for COVID, for instance, you take into account age because, well, the case fatality rate is much higher for elderly. So if you are trying to study aspects like I have a model and I want to look at use the model to somehow study the number of diseases people, you have to take into account the age of the people. Okay, so there are models that are structured by age classes. From each class has from 0 to 5, from 6 to 10, and so on, which has lots of class ages. But you can also do something. You say from I just want children and young people from 0 to 18. Then I take the other class. I take just adults from 18 or 20 to up to 50 or 60, and then I take elderly because so you can do a simplified model with only 3 class ages if you want, for instance. Okay? Now the example I want to give you today has only 2 classes. Okay? And this is adapted. It would be better, it could be applied to sexually transmitted diseases, where clearly you can have 2 classes. When one is high risk and other ones are low risk. Okay? So high risk are people that have many partners and have many contacts, okay, and low risk is people that have just a few partners over a certain period of time, okay? And then there are people that can use protections like condoms and so on, or people that don't. Okay, so the model I will write down here is actually better for either men that have sex with men or women that have sex with women, because I won't make a distinction between men and women in this case, which should be another two classes. Okay, so in order not to do this, what I will be discussing here is just two classes of high risk and low risk without looking for if the person is the sex of the person. So it would be better fit for this case of homosexual relations. Okay, so how can I do this kind of thing? So I can divide my population into classes, therefore, let's start with a very simple model, which is just on the model that we discussed in the first class, which is the SIS model. Okay? So SIS, like, where people can be susceptible, infected, and once infected, they go back to the susceptible class. Okay, could also, so this is, it's more or less, I mean, we are not, if we took the case of HIV/AIDS, for instance, that then you don't get back to S. Actually, you stay in I forever. So, okay. And so now, if I look at this, and I will have high risk and low risk people. Okay, so I will have compartments for S high risk, S low risk, right? And I high risk and I low risk. Therefore, I have to have 4 differential equations for the situations. 4. Okay. So, and how do we proceed? We will proceed as we have proceeded in all cases. We'll write the equations like we have this here, high risk, then we have this low risk, then we have high risk, and then we have low risk. And let's do the simple thing, okay? So first, let's model how people did the contagion situation. So how do you become, I mean, you are susceptible and you are high risk. How do you become infected, okay? So if you become infected, you have had contact with people either infected from the high risk or the low risk group, okay? So the groups connect, right? But so we are assuming that your behavior is fixed, okay? A high risk person doesn't take any action, say now I will leave the high risk group and go to the low risk group, okay? But they can have contacts with both. Okay? So what would you expect? You would expect that, for instance, you have some infected of high risk, okay? And then how many new infections will this group of an individual of the high risk group create? That will be something proportional to the number of contacts. We are not taking into account here that people have a distribution of contacts. We are looking like that. There's an average number of contacts. But then you need to take into account also the frequency which this person has contacts with high risk susceptibles. The contact rate between susceptibles of high risk and infected of high risk. And I will call this C ash ash. So high risk with high risk. Okay. And then once you have a contact between high risk and other person of high risk, then you need to take into account the probability that this high risk person actually is susceptible, not infected, which will be something like S high divided by N high, where N is the total number of high risk people. And then there should be some probability that once you have a contact between high risk people, high risk infected and high risk susceptible, that it actually will create a new infection, okay? Which is, I will call it beta. Okay? So you don't have all of this. Okay? So this, I will do a simplification for notational. I will call beta times C ash ash K as beta ash ash. Okay? Good? So instead of writing this, I will write beta ash ash S ash over N ash. Nice. Okay? Well, and then the rest is the same reasoning that you have. So this beta is not exactly the contact matrix because it has already the probabilities of infection, and it has also the total number of contacts included. So with a minus here, okay? And then you can also get infected with a contact with a low risk person, infected person, that will be beta L ash, which is S ash over N ash I L. Okay? So this takes into account that you have a person of low risk infected, which has a certain contact and certain probability of infection, L ash, times the probability that the person that is being contacted is actually a high risk person. Okay. So, and now for the next equation, it's just the same thing. So you will take minus beta ash L as L over N, total number of low risk, times the high risk minus beta LL as low risk N. Is that okay? So you have two classes. The classes have contacts, and you can have infections of high-risk people due to contacts with high-risk people and low-risk people. It's the same thing. The low-risk people can get infections due to high-risk people and low-risk people. Now, for here, it's simple. All the high-risk people, infected high-risk people, originate from high-risk people that were susceptible. Okay? So that just takes all of this here, okay, with a positive sign. And then you have the same. Okay, so this is the contagion, the transmission process. Now we have also that people in the infected class remain for a certain time in the infected class and then go back to the susceptible class. So then there will be some gamma here and proportional to I index high. And I will suppose that the gamma, the time you spend being sick, it's the same for high risk and low risk people. So the disease is the same for. So you have this. And they go back here plus gamma IH. And that's it. Right? So you have 4 equations which have transmission terms and recovery terms. Right? I will suppose that beta I would suppose symmetry. This is not mandatory. You could have that the probability of infection given a high risk infected person with a low risk infected person is different than having a low risk susceptible. It's different from having a low risk infected and a high risk susceptible. Could be. But let's simplify our life here and say the probability of getting infected is just proportional to the state of high and low, and not who is the infected and who is the low one. Okay. So water. So nice model. Now, how can we proceed? What would you like to calculate with this? So the first thing you'd say, I want to know R0. Okay, well, that's what we usually want to know. Right? So I won't calculate R0, but it's a lot of algebra, okay, and so on. But the point is, what I want to mention here is something that is valid beyond this kind of model. If I want to calculate R0, I want to know if I introduce an infected individual, a very low number of infected individuals, and if the number of infected will grow. Okay? So then I would usually say I will look for the infected classes, and I want to know if this is positive or not. That's the way this you play this game. Okay? And then you suppose that you are initially susceptible population. Right? Then you will say this is close to 1, this is close to 1, S over N. All the S over N are close to 1. And then you get an equation which only involves I index high and I index low. But they are connected, both of them. Okay? So you have we'll have 2 linear differential equations. but coupled. Okay? And then you, if you are more mathematically minded, you know what you have to do. You have a, we will have to calculate an eigenvalue and know if the eigenvalue has positive real part or not. That's it. Okay? And yeah, you can do this. So you can do this, and I mean, you can, and in this way, you will calculate R0 as the condition that the disease-free state is unstable, right? So if you are disease-free, you introduce some infected people, then it grows. Let me just mention that this procedure can be used in many actual problems. So many problems in epidemics have this kind of structure. You have the disease compartments. Here we have only two, which is infected high risk, infected low risk. But you could have, for instance, people that were exposed but are not infectious. You can have latency, latent period. You can have asymptomatic persons. You can have many kinds of compartments. But you can surely divide your problem between compartments of people that are infected and people that are susceptible or renewed or removed. Okay, so, and it is most of the time true that you will have this kind of situation where you have the infected compartment, and then you will take the susceptibles to be nearly fractions of susceptible, nearly 1, and then you get a system of equation for only the infected compartments, which will be linear, and you have to calculate eigenvalues and so on and so on and so on. Okay? So you can do this for many situations. Okay? And then you can formulate even this like more formally. Okay, say the infected compartment is something like a which has a linear dependence here, and so on and so on. And you can go on with this, and this means that for many situations you can actually calculate R0 for, even if you have more equations, you only need to look for the infected compartments. Okay? This is, and this gives rise to, I mean, this has been more put in a more formal way, and this is connected to, if you are interested in how to do this, you can Google or look for something which is called next generation matrix, and the best place I know, it's in this book here. It's called Mathematical Epidemiology, which is and there's a chapter by Pauline van der Drische, which gives you everything you want to know about how to calculate R0 in compartmental models, and using this idea that the actual important compartments are only the infected ones. You don't have to take care about all the risk. Right? Beautiful, beautiful, beautiful. Okay? So I won't do anything like that. Okay? Because why? Well, it's a lot of algebra and so on, so on, so on. But what can we do which is more? I mean, we can play with this equation. Let's just look for the solutions numerically. Okay? So you can play with, because here you have some questions that you can pose. You can say, if I introduce initially an infected individual in the low risk compartment, will it be different from the case if I introduce in the high risk compartment, for instance? And one thing that you could do, if you look at this, just before going for the numerics, you see, if say the low risk compartment, everybody is high risk. Okay, let's go for the extreme situation. We don't have low risk people. Then this case here, this equation here, let us call it equation A here, will be just this. And at the very beginning, this will be 1. This will be I index high minus gamma index high. And then if beta high minus gamma is bigger than 0, meaning that beta over r high over gamma is larger than 1, this I would call this R0 index high, and then you would have the epidemic in this situation. And the same thing for equation. If everybody is low risk, then you would have something like beta LL over N over gamma bigger than 1, then you have an epidemic in the low risk population. So one thing that's intuitive is if both R0 for the high risk group and R0 for the low risk group are both bigger than 1, then you expect to have an epidemic, because you would have an epidemic with in any situation. Okay? So the interesting thing is now to consider that the high risk group, and high risk means people have more partners and so on, so on, so on. You expect that this guy here is bigger than this guy here. The interesting case will be when this group has an R0 of the high risk group is bigger than 1, and the low risk group is smaller than 1. Will we have an epidemic or not? This is the question, okay? And will the epidemic in this group spread to this group? If we have epidemic, will it spread? Will it spill over to the low risk group? Everybody will get infected or not? Okay? So this is the question. So, and we can play with a nice code, with the adaptation of Renato's codes actually, for 4 equations. So let me see how to get the computer. Yeah, nice. Okay. So here you have a simple Python code to study this population with risk. You can, yeah, I don't know how to do. I'm very bad with. I never use Windows, and so I'm completely lost here. Okay. Control mice. Yeah. So the things goes, so you have to have numpy, matplotlib, and scipy as usual, okay? Then you say I will do my integration from 0 time 0 to time 15. We will be playing with that later. And the time steps is 0.01, okay, small. And we'll have a lot of parameters. The parameter high is the beta high. I mean, actually, yeah, beta high. LL is beta. LL HL is the beta. The cross contacts. Gamma is gamma. So here I'm in a situation where the high risk group has, I put 0.9 compared to 0.3. So this means that this guy here is bigger than 1, right? It's actually 3. Okay, 0.9 divided by 0.3. Okay? And this guy here, the low risk group, is 0.2 over 0.3, which is smaller than 1. Okay? So I have a population. The low risk group would not be, say, invaded by the pathogen if there were only low risk people. So then I have to put some number for the total population. I'm supposing that the total population is 100,000 people, and I have a fraction of 5%, which are high risk people, and 95% that are low risk people. When I wrote this code, I've put a B here, but it's equal to 1, so you don't care about the B. Okay. Yeah. That was because I had a contact rate times beta, but later I decided to put the beta into this beta high, low, and so on. So you have to give an initial condition, and I have 10 people in the high risk group which are infectious, and no one infectious in the low risk group. And then you write down the equations. Okay? So the first equation is, as I told you, this B is, at the end I put it equal to 1, so never mind about this. So this is beta high times x 0, which is S high, times x2, which is I index high, divided by the number of high infectious people. It's just the first term of the first equation. Then the rest follows at the same way of formulating the things. You have beta high low times S high times S low. So my vector is x is given by S high, S low, I index high, I index low. Okay. So this is x0, x1, x2, x3. So you write down the equation, then you ask it, you integrate the equation, you plot the solutions. Okay. You don't want to plot all the 4 solutions on the same plot, actually. It's too many things. But let us just plot some of them. For instance, the infection curve. Okay? The infection curve. So I will only plot the less two I index high, I index low. Okay. So if you do this, so what do you expect? This is an SIS model. If you remember well, the first class SIS models were the ones that you grow and you saturate. You don't have a grow and they grow and saturate. So they go to an endemic state. Okay? So let's look what happens here. And here you have the. So if you look at this, there's a problem of scale, obviously. The high risk group has at the end the endemic state is it's almost 70% of the high risk group being infected. Okay. Okay. So just a moment. I divided here the low risk group, the high risk group, by the total number of high risk people, and I divided the low risk group by the total number of low risk groups. So I'm calculating the relative values. Otherwise, that would be. I mean, this gives you more like the incidence per capita in each group. Okay, so. So you have an invasion, more or less like you would predict for the total number of infected people in the high risk group. The low risk group, it looks like it's 0, but if we plot only the low risk group, so let's comment this guy here. You see that the oh, but no, I commented completely. Okay, that's the low risk group. Here, don't pay attention to this legend. Okay. So it's very low prevalence, very low. Let's plot it for a longer time. Let's put 100. So it also goes to a state which is an endemic state, but a very low endemic proportion. So this would be 0.3%, okay, of the population of the low risk group getting infected due to the contact with the high risk group. So you have a high risk group, you have an epidemic in the high risk group, and then you have some spillover to the low risk group. But this is just you can think it's just the contacts of the low risk group with the high risk group, and it's not propagating in the low risk group actually. Okay. And you see, this should obviously depend on how much contacts I have between the high and the low risk group. So if I multiply this parameter, the beta high low, by 10, for instance, I should have a higher endemic equilibrium value for the low risk group. Okay, so I have more contacts, you see, and then it's much higher. Now it's 3%. Okay. So then you could also say, okay, and if I let's go back to this case here. But let's say that the low risk group has its own R0 defined in this way, also bigger than 1. Then you expect also it to be invaded. So this is, beyond this small endemic state. So let's say it is O4. So everything depends on the relation between the beta, which is beta LL, in this case, with gamma. Okay, so if this is bigger than the gamma, then you have R0 bigger than 1. And you look at this, and yeah, you see now you have 25% of the population. Okay, if you look, and you can plot. Yeah, there is contact between the population. So that's true. So that's why in the previous example, there was some people from the low risk group that actually got infected by because they had contact with the high risk group. If this were 0, then there would be no contact. Yeah. So and so this is the what people call the transmission matrix, like this one. Yes, beta. This matrix, which the transmission matrix. Okay. So this matrix actually incorporates behavior in this case. Okay. So what we are saying that the high risk group has a beta. It's higher than the low risk group, as in the example. Okay, meaning that high risk is actually a translation of having many partners in this case, and low risk group is means that this is small. Okay, so the low risk means that beta is small, okay? And this here is a quantification of the contacts between the two groups, because people are not completely separated. Okay? So if you think now, let's say you could think in a different way. You think I have a network of contacts. I have a network of contacts. Okay? You have people here, 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 here. A lot of people. And then you have maybe people that you will call high risk guy here, high risk guy here, high risk guy. Okay. High risk means a lot of contacts. In this simple example, I have these guys here have lots of contacts. Well, this not so much actually. Yeah. Okay. Let's put this here. So this has 3. This has a lot 1, and this has also a lot, and the rest has either 1 or 2. So this would be a network that you could build. If you know the contacts that people had, okay, over a given time period. Usually use 1 year. So okay. So, but you never get this contact network, because it's not easy. How would you obtain this contact network? You have to ask people. Okay? So people won't answer in general, okay, because it's an intimate problem, and they don't trust it. If you are going to make an interview, they say, I don't know who is this guy, and how do I trust him? Maybe he will tell my wife that I cheated her or something like that. So I would say, no, I don't want to answer, okay? And then there's also the problem that sometimes the very high risk group, which could be people that sex workers, for instance. They don't know the names and the people that they had contact. Could also be people that go to these big parties, which are kind of orgy and so on. They don't know. They don't know it. The people that had contact. So even if they are willing to answer, they can't. So you don't have this. Okay? So this would be an ideal case, but and then you could say a person can be susceptible, can be infected, and so on, and then you could run this a kind of model here. Could be a stochastic model, could be whatever you want, or even a deterministic one. And then study the problem fully. But usually you cannot do this. So the way I'm proceeding here is a way to incorporate two types of behaviors. Here you have more than this, actually. You have this guy has 1, 2, 3, 4, 5, 6, degree 6. This one has degree 3. This one has degree 3. This one has degree 3 also, so he should be maybe this one. This has 1. This has 1. This has 1. This has 1. 1, 1, 1. Okay? But you could have intermediate cases with 2, for instance, here. This is 1 and this is 2. So you can have disconnected part, connected part, and everything you want. So I'm taking this whole complexity and saying 6 and 3 is high, below 3 is low. Right? That's not perfect. That's not perfect. And here you have actually people for low contact with high, and you have also all the high guys are connected. Okay, so this is a network, and what we are saying here also is when I say that beta high is larger than beta LL and beta low high, it takes into account that this network here displays a property which is called how it's called assortativity. So people of the high risk group have a higher probability than contacting people from the high risk group than contacting people from the low risk group. Right? So this takes into account behavioral factors. It's behavior, because I mean you could have just random contacts, but people don't have random contacts. In mainly, if you think about sexual transmitted disease, that contacts are far from random, and then you have people that will stay in the behavioral class of them. They will have preference to have contacts with people that are in the same behavioral class as themselves. So all of this could be done in a much more precise way if I have the contact network that I don't have. Here I made a simple simplification saying, okay, I have high and low, but in the contact matrix, in this beta here, I can actually put some behavioral facts into it. Okay, so saying this is very high means that people that high risk behavior tend to be in contact with other people that also have high risk behavior. Okay, and you see, this is the case that when we made the numerical calculation. Sorry, I'm where in this case, you can define separate R0s for the high risk group and the low risk group. And obviously, if both of them are bigger and smaller than 1, then probably you won't have any invasion. Okay, I mean the high risk group and the low risk group, both of them have R0 smaller than 1, then you don't have an invasion. But if you have one of them bigger, and this is the high risk group R0, then you have actually a population that an epidemic which spills over to the low risk group, which would usually not be invadable, spills over, but spills over at a low endemicity level in this case that we studied. Yeah. So this is an example of translating behavior into a matrix of contacts, which takes into account the behavior and the number of contacts and so on. What could you do better? Well, if you go back to this one, you can do a histogram here with the number of contacts being 1, 2, 3, 4, 5, 6. Then you have one contact, you have 1, 2, 3, 4, 4, 5, 6, 7. So you'd have 7 here. Number of contacts 2 is just 1. Number of contacts having 3 contacts, if we have 3, 1. Number of contacts equal to 4 is 0, 5 is 0, and 6 is 1. Okay, so you have a distribution of the degree, the number of arrows that connected to a certain point. It's called the degree. Okay? So you have the distribution of the degrees. Then you could make a model in this case with 1. You could make a model with the number of compartments equal to the number of the degrees that you have in your distribution. Okay. So, and how would you do this? The same argument here. Just go on and you will have a contact matrix between all the groups. Okay? The point is, knowing, I mean, if you do it in a more, more detailed way with all the possible contacts, then all possible degrees, then you have more equations and you have a bigger matrix of betas. You have beta 1, 2, beta 1, 3, beta 1, 6, beta 2, 3, so lots of betas. Okay, and so maybe it's difficult to parameterize this also. Okay, could be more complicated. Okay, so but anyhow, now this network here, you usually can't get much information about it. Okay, but this network, it's this degree distribution can be easier. Why? You're just asking people how many contacts they have over a certain period of time, which maybe people would tell you. Okay, so they don't have to give names and so on. So the people would say, okay, I had 5 contacts, I had 5 partners, I had 6 partners. Okay. And then there's this distinction between partners and the number of actually sexual encounters, which can be connected, but different questions. Okay? It's easier to ask for the number of partners. Okay? So, but with this, you can already start to build some kind of models, but with a big beta. So then you have to know the frequencies of contacts and so on. That this is obviously not so easy, but it's a way forward. Okay? So, what do you think would be a good way to obtain information about the number of contacts? How would now you got a new job, and you work in a health institution, and people say, okay, we want to do a field research, and we want to know that how many sexual contacts of a certain kind people had in a certain territory. How would you proceed? Ideas. Yeah. So the first step is ask people. And then at the end of the day, so I don't know, and many people didn't answer. And can I actually trust what people said? No, you can't trust. Yeah, you have an expectation that this is usually decaying. I mean, this is usually decaying. Most people have only one partner, and so on. Not necessarily a parallel law. Could be an exponential decay also. Actually, there are you know, in England, in UK, it's very good for data. I mean, they count people and what people do and so on, and they have actually distributions like this. And turns out that some it depends on if you are looking for homosexual, heterosexual, they have more like power law or more like exponential decays. Okay. But okay, so that's what you expect. But okay, your job is not expecting anything. Your job is go out there and find a way to know this distribution. So how can you improve your thing? Yes, actually. So what you're saying is okay, you go out and ask people, but then you do some statistical data analysis in order to. But you need to have some knowledge about the biases and so on previously. Okay, yeah, that would be one way. But that's what else? I mean, very pedestrian approach. What could you do? I mean, you are not alone. Huh? No. I mean, there's a group of people there to work on that. What could you do? So let me tell you a story because that's a real one. Actually, it's not about sexual context, but it's this is a guy that used to be a professor of the University of São Paulo, and Elda Nakaya. And before the COVID pandemic, we used to have some seminars at the Institute of Mathematics of the University of São Paulo, and he was invited. And he's not a mathematician. And I think, I don't know, Nakaya is maybe a medical doctor. I don't know. Okay. Anyhow, and he worked with risk factors for malaria in the city of Manaus in the north, in the Amazonas region, in the Amazonas state. So he wanted to know, you have a big city here, but obviously you don't get malaria in center. You get malaria in certain places. So I want to know the places which are actually the places where people get infected. So I have to know from the people that get to the health facility with malaria where they have been, right? Which are the places that they have been. So I need to know their previous movements. Okay, so then what did he figure out? Okay, I will ask people permission to get their Google data, the data from Google, their personal data about their movement. Okay, so if you do it, that's a good idea actually. And actually, at first it didn't work because people said, "No, I don't want to give you my data. Why would I give you my data? I don't know you. I don't trust you." But then he took a person. He put a person which was actually a physician, equipped with with the white and so on, looking like a physician, and people actually agreed to give the data because they trusted physicians, not other people. So the idea is it's nice to follow people, but you can have problems and people actually allowing you to follow them, because I don't know, people have maybe weird sexual life and they don't want to expose this, and even if it's not sexual life, it's malaria contact, which actually, but the people was afraid. I mean, I don't know, maybe the person had a kind of second life and so on, and it will be obvious if you follow the person. So people won't share this easily. Okay, so more ideas. We need more ideas. That yeah, yeah. The contact rate, but I mean, if you say, okay, I will just follow the number of condoms that are being sold, but you don't know the number of contacts of the people. I mean, I don't think people use the condom more than once, but anyhow, you'd have to know more details. Okay. Yeah, will be like, oh, I don't know. Yeah. Because most of the time, the reaction of people would be, I only have one. So difficult. It's nice theory, whole lots of equations, behavior into the equations, everything goes. But how you get this fucking data? Okay, this is really difficult in these cases. Okay. So let me tell one experience that I know from a friend of mine, actually. She's an epidemiologist and field epidemiologist, Maria Amelia. And so this person works with transsexuals, usually poor people, poor transsexual people that live in most of the time in the center of downtown of São Paulo. but not exclusively downtown, but anyhow. So one way to approach these people is if she goes there and asks the person, they say, "Where are you? I don't care. I don't want an answer." But she has a team, which are also transsexual people. And many of them had been poor or sex workers and so on. So creating a team can lead people to say, "I have some empathy with you and I will answer you because you are like me." You create a team of people. And then you ask these people if they can also help asking other people. This means also that you have a questionnaire. It should be sufficiently simple. If you give them 10-page questionnaire about the whole thing and everything you want to know, people will say, "Okay, that's too much." But asking some specific questions is easier. So you can use this kind of tactic, and then you do also a lot of statistics on it. It's called the snowball statistics. And then you use the fact that people will trust people that interview them because they feel somehow that they are from the same class, let's say. Right? So this is a way that that actually people proceed. And building this kind of team, it's difficult, and is actually very valuable. Okay? You're having set up, you have a population, and you have a team that you can study, and you can study many aspects, and so on, and so on, and so on. It's actually an asset from the point of view of research. So this is just one example of how all of this is very nice. You could start with a network, then it turns out you cannot have the network because, for instance, what this friend of mine does is it's the number of partners, not okay? They had contact. The number of partners, so you can have the degree distribution. With the degree distribution, you can already start building some kind of model. Okay? So you can show, for instance, if you have a degree distribution, so you could have something like that. Okay. You could go very fast to 0, or you could go not so fast. And mathematically, this means that you could have an exponential decay, or you could have a polynomial decay. The polynomial decay depends on the area. People call it a fat tail, or a Levy flights, or whatever. There are many names for that. And one thing that you can show, if your decay is polynomial, then it's much easier to invade the population. But what means that the decay is polynomial? You mean that here, far from the beginning, you still have a small number, but still a representative number of people that have if you are talking sexual contacts in this case, that you have people that have like 100 sexual contacts per year, partners per year. Okay? So, and if it's exponentially decaying, then probably you don't have this, guys. Yeah, I mean, all of this is an idealization because all of the real degree distribution are finite. Okay, nobody has thousands. Okay, so they are finite, but they are approximated how fast they decay. And if you have a polynomial decay, then it's much easier to invade this population than if it has an exponential decay. And this is, yeah, I mean, this comes back to the kind of research that Renato was mentioning, for instance, about contact matrices and between ages. Okay, So that would be a social, a problem of social science, okay? A quantitative social science. And here that's also kind of problem, which is kind of health and social science thing, what you have to investigate this. And that there are not many data about that, actually. And something else is also important. When you have this kind of situation here with polynomial decay, and sometimes you also have the situation that we discussed here, which was that the betas here, we have the betas here, and we kind of coded behavior into the betas and saying that, for instance, this is the biggest one, means that these people have more contacts and they have more contacts between them. So this is called a property, I already mentioned, assortativity of the network. And what happens if you have assortativity is usually that the spread of the epidemic will be I mean, if you have this kind of polynomial decay, it's easy to invade, but the tendency is to stay at the high-risk group in this case, okay? As we saw with our numerical example. That's it. So you can do things. You can do theory with still doing compartmental models, which get some aspects of behavior through this kind of matrices. The usual difficult point is this matrices of, in general, contacts, either sexual or contacts by just being near the person, or for some respiratory cases or whatever. Contacts are difficult to measure. Okay? So it's difficult to have the actual contact matrix. Okay? And then there's a second point, I think, already at the end. For sexually transmitted diseases, it's easy to know what's in contact. Okay? But for other diseases, it could be difficult to define contact. What is a contact for a respiratory disease? Okay. And then there you have things like cholera, where you don't have contacts between people. You have environmental contamination, contagion through environment. Then all of this kind of thing more or less collapses. How you don't have contacts and so on. For vector-borne disease, you have contacts, means the contact of the mosquito with you, but you, not only mosquito, it can be ticks or can be anything else. Let's say it's a mosquito, but then you don't have the demography of the mosquito, okay? Mosquitoes don't have addresses where you can go there and see how many people live in the household. So then you have a problem with having demographic. I mean, just knowing the number of mosquitoes in a certain region is difficult, okay? And how they fluctuate. How do people actually proceed? Is with mosquitoes is doing calculating something that's called an infestation index. It's not the total number of mosquitoes, then you never know this, okay? But you could have a proportion. I mean, you have a low season, a high season, and so on. You put traps, which can be simple traps, okay? Just kind of paper with some glue, and people the mosquitoes gets there, cannot leave, and then you count the mosquitoes in this species, and then you use this kind of this index in order to try to evaluate at least the relative sizes of mosquito populations and so on. But anyhow, usually it could be a problem to define contact, and this is actually, I think, one of the big problems with this kind of models of individuals that have contacts and the whole networks. It's nice that you can play a lot with this. You can put different kinds of networks, scale-free networks, Baravasi networks, or whatever. Nice, and then you can study, and people have studied, and very nice papers, very beautiful work. But then you say, okay, this is nice, but I'm in the Department of Physics or Math. Now I go to the Department of Public Health at my university, and they say, okay, but we don't have the network. Okay, that could be happen very often. Okay, and so this poses a real problem for. But there are other networks that you can have. For instance, if you're talking about movement, then it's easier to have data about movement. Say roads, and then you can put weights. This is São Paulo, and this is Santos. They are super big. Then you put a weight on this arrow here. But this is São Paulo to, I don't know, give me a small Botucatu. Say, then this has a different weight. You can have weighted networks, and then you can also do the things. So for spatial spread and for global problems, you could have the airline networks and the number of passengers on each route and so on. That's possible, and that's actually a network that you can work with. It's things that people do actually. But the real contact networks are much more difficult to have. Okay, so I think that's it for today. And any more questions or comments? Yeah. Yeah, that's a difficult here. The way I build this is for sexual contacts and so on. I think that's a good way to build. But remember, with Renato's discussion, there can be different options depending on, for instance, for age, structure, and so on. And also, you could say, you know, this contact here, people, if people have the sexual contacts have a real way of distribution, but just say that now it's instead of high risk, and it's age. That you could say, well, people have more or less the same number of contacts, and but with different classes. Then you could also say, okay, they have say 10 contacts in average, and there's a certain probability of the transmission, the beta, and then you have the matrix. And if the contacts are completely random, you'd say that the number of contacts are proportional to the size of the population in that class. Then if you work it out, then this guy disappears and you get an N here. So completely random work. But well, this is the case where we would have really completely random contacts, and just saying that the probability that you have contacts between classes is proportional to the sizes of the classes, right? Which it's a way that you don't put behavior into the problem. Here, in this betas, we are putting behavior. You're saying that it's not just because I have a lot of people in a certain class that I have a lot of contacts with these people. For instance, a high risk individual has more contacts with other high risk individuals, irrespective of the size of the high risk individual's class. They're usually smaller, so then you have this kind of situation. But you can have also other kind of situations when we are talking not so much about behavior and just random contacts. Yeah, more questions? Yeah, you and then you. Mm-hmm. So I mean, the network or the degree distribution. You could use the degree distribution. Okay, you have as many groups as many degrees, non-zero degrees here. That you could do, okay? But then you have a proliferation of betas. Huh? So, is it really important to distinguish the person that has one from the person that has two contacts, or not? So, depends on what you are studying. Okay, it can be relevant or not. So you can use, you can instead of 2, you can have 10, 20. It's possible. Okay, but then when you have the problem of with what you do with the for your matrix. I mean, you now you assume I have the network. Okay. Okay, then you can calculate obviously the relative proportions of the betas. But then these betas are not only the number of contacts. Then but the proportion of contacts times the actual number of contacts times the probability of infection, which is was the beta without index before. So the probability of contact. So at the end, what we supposed here that the probability that given an possible infectious contact was independent of the classes, okay, of the betas, in the sense that, but could also depend. So this can give you the proportions, but it depends a little bit on if your probability of giving a infectious individual and a susceptible individual, if this is independent of their states or not. Yeah, you linearize this. I mean, you suppose that something like that they have two types of classes. You have the infectious classes, say X, okay? And then you have the non-infectious classes I. So then they have this equation will be something which is some F. It depends on X and Y vectors, okay? Which is all the cases that come from the contagion minus something. This is usually this, which can depend on X and Y, but usually depends only on X, which is the outflow of the class. Okay? So if you can have this in this way, then you take at the beginning, you will actually suppose these guys here are close to everybody's susceptible, then X is small, and you linearize this, and then you will find an eigenvalue problem with F, linearization of F and linearization of nu, which will give you, and then you look for the highest eigenvalue, more or less like this. So the next generation actually, so it's given in terms of the linearization of these ones, but I can't remember now exactly how this looks. You remember this? It's kind of yes. Yeah, this will, if you linearize this will give you some different f, okay, let's say times x, okay, so a matrix of linearization of this, and then you have, this is usually linear, okay? So we will have f minus nu v or v, I mean, yeah, okay, they use u, so equal to 0, and yeah, no, not equal to, okay, you will have this.
But then you have the f times the inverse of v.
Yeah.
This is the next generation.
Yes, the f times the inverse of v.
F times the inverse of v.
Yeah.
The inverse of v gives you the expected waiting time.
Residence time.
Residence time, yeah.
Yeah. With one dimension, that's what's clear, because you had this divided by f divided by v. Okay, so it's a matrix version of that simple fact before. Yeah. Okay. Anything else? So we have time for coffee break, but before coffee break, let me just say. So how is will be then the activities this afternoon and tomorrow? So this afternoon is group work as usual. I think it's good time for you to prepare also the presentations, okay? I would not suggest you to build a new model today. Okay, so you have what you have, and maybe you will be analyzing things. I mean, ideally, I know people that stays until midnight with new models, but okay, that's up to you. So the idea is that you prepare the presentation for tomorrow morning, and we will start at 9. But please, tomorrow at least, be here at 9, because the idea is we will only use from 9 to 1 p.m. Okay, 4 hours. Okay, so in this way we have the free afternoon. Okay, but we have to start at 9, otherwise this 1 p.m. will be 2 p.m. We will hungry and so on. It would be a disaster. So you have to be here at 9. Okay, and it's also nice to be here at 9 with respect to your colleagues that will be presenting. Okay, nobody wants to present for a empty room. So, and every group has a time slot of 30 minutes, which is to be used like a presentation of 20 minutes and 10 minutes for questions. Okay, so prepare for 20 minutes. Okay, there's some space for 1 or 2 minutes more or less. Okay, so it's not so every group have half an hour, a total half an hour, 20 plus 10 for the presentations. Okay, so you have the free afternoon tomorrow. Okay, I think that's all. Half an hour coffee break, yes, because I have to look for that. I don't know. Good question. I have no idea. There will be a half an hour break. Yeah. So if we start, it's maybe a water break. Water. Oh yeah, yeah. It's not a. But the idea is that you have 3 presentations from 9 to 10:30, which would be the usual time for the coffee break. And if you have coffee, good. If you don't, we just make a small break, and then we start again at 11. Perfect. Oh, okay. Thank you.